So this is section 9.4. This is the last section in chapter 9, and this is on counting techniques in probability. So let's suppose that on a trip you pack 2 pairs of pants and 3 shirts. How many outfits are possible? Well, we can draw a tree diagram to kind of help with this. So we have 2 pairs of pants and 3 shirts. So each pair of pants can be matched up with 3 different shirts. So there are 1, 2, 3, 4, 5, 6 different outfits, assuming that you decide to wear pants with every outfit, which, I don't know, I'm not judging. Maybe you don't want to. So there's 6 different outfits. Now, we could have found this a lot quicker without having to draw a picture here by just simply multiplying 3 times 2. This is what's called the fundamental counting principle. And it says the number of ways in which a series of successive things can occur is found by multiplying the number of ways in which each thing can occur. So, for instance, in the above situation, number of pants, number of shirts, 2 times 3, 6. So remember in the last section when we did the tree stuff, that we had like 8 different outcomes for the gender of 3 different children. Well, 2 times 2 times 2, right? We have 2 choices for the first child. We have 2 choices for the second, 2 choices for the third. Okay, so let's look at another example here. A discount paint manufacturer plans to make several different paints. Here are the categories. We have the different colors, the type of paint, the texture of the paint, and the use, whether it's indoor or outdoor. So while this may look, let me put a comma right there, while this may look really convoluted, it really is not. Okay? We have 1, 2, 3, 4, 5, 6 different options for color. We have 2 options for the type. We have 3 options for the texture, and we have 2 options for the use. So how many different arrangements are there? How many different, if you have to pick one from each category, how many different kinds of paints can you make? Well, we're just going to take 6 times 2 times 3 times 2 using that multiplication principle there. And let's see, what is that going to be? That's going to be 12 times 6, which is 60, 12, 72. So 72 different arrangements, assuming that you pick one from each category. A keypad has buttons labeled 1 through 5 and requires a 3-digit code. How many codes are possible if you can repeat digits? Well, we're still going to use the multiplication principle. Now why? Because these things are happening in a series of successive things. So something's happening and then something else and then something else. So remember how I said that in probabilities and means multiply and or means add. Alright, so we've got a 3-digit code. So let's say that this is the number of choices for the first digit, there's the number of choices for the second, and that's the number of choices for the third digit. Each digit has 5 choices, the numbers 1 through 5. If they can be repeated, then you get 5 choices for the first, 5 for the second, 5 for the third. So we get 125 possible codes that are possible. Now, if the digits can't be repeated, okay, so let's say that one's the first, there's the number of choices for the second, number of choices for the third. Here I've got 5 digits possible for the first one, but if I can't repeat any, once I use this digit, I can't use it again, so now I only have 4 digits to choose from for my second digit. Once I've used these 2, I can't repeat it. I can't repeat either one of them. So I'm down to only 3 choices. So let's see, 5 times 4 times 3, that's 20, times 3 is 60. So we certainly have a lot less options. So you need to think about this as in passwords, right? Like how many different passwords are possible if you can repeat digits, if upper and lowercase are treated differently, things like that. So you can see how many more options we get by allowing that repetition. Now, before we get into these other arrangements, let's look at something called a factorial. Okay? A factorial is this exclamation point. Okay? That's called a factorial symbol. So this is actually read 5 factorial. So that's how you would read that. You don't read that as 5. You read that as 5 factorial. That symbol is on your calculator. Let me grab my calculator out of here. And it is under math and then probability. You can see option 4 there is the factorial. I need to put a number in there first. So 5 math probability option 4, 5 factorial. That factorial symbol is the abbreviation for this product of all the numbers, all the natural numbers from 5 down to 1. So you can see 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial is the abbreviation for 4 times 3 times 2 times 1. 3 factorial, 3 times 2 times 1. 2 factorial, 2 times 1. 1 factorial, 1. So, following this pattern, what do you think 0 factorial is? I know what you're thinking. You're thinking it's going to be 0. Wrong. It's 1. Well, number 1, we'll see why later. Also because it's a definition. And we'll see why it's defined to be that later. But just in case you don't believe me, you know, just in case you're like, yeah, she's an idiot, doesn't need to be teaching anybody. Oh, look at that! 0 factorial is 1. Great mysteries of the world. Area 51, Stonehenge, you know, the Easter Island, crop circles, how to fold a fitted sheet, 0 factorial. All these great mysteries of the world. Not really, it's just a definition. We'll see why in a minute. Okay, so if we're going to simplify these, you can use your calculator for most of these. Okay, so if you want to use your calculator. Now, something to remember, and that is that factorials, you can't cancel them. So you can't just cancel out that factorial symbol and just say, oh, the answer is going to be 3. I wish. That'd be so much easier. But it's not. You can use your calculator, but let me just show you how it's gonna kind of shake out here. 9 factorial is going to be 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. And then 3 factorial is 3 times 2 times 1. Once I get rid of the factorial symbol and I expand all of that out, now I've got nothing but straight multiplication. Now I can cancel stuff. I can't do that here because I still have the factorial symbols. So my answer is just going to be that 9 times 8 times 7 times 6 times 5 times 4. So 9 times 8 times 7 times 6 times 5 times 4. And we get, what, 60,480. Got a little bit of a glare there. Sorry about that. Now, if you wanted to put in the original problem, you could. So the original problem was 9 factorial divided by 3 factorial. So either way. So this is just showing you the behind the scenes action of what your calculator's doing. This one looks really tempting, right? You kind of want to be like, oh, 2 times 5 is 10. That's going to cancel, and you're just going to get 1. No, that's not how it's going to shake out. So let's just write all this out. Here we got 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And that's over 2 times 1. There's the 2 factorial. Times, because of the smushing there, 5, 4, 3, 2, 1. The 5, 4, 3, 2, 1s are going to cancel. So all I'm really going to have to do is take the 10, 9, 8, 7, 6, multiply those and divide it by 2. Now you can even go a step further and say, well, 2 goes into 6 3 times, and then just have to multiply that stuff out. So let's see what we get here. So 10, 9, 8, 7, 6. It's 30,240 divided by 2. And I got 15,120. You should do these on the calculator with me. Don't just watch. You should grab your calculator, pause the video, and be doing these on the calculator with me so that you can figure out, if you're able to do this on the calculator. And if not, you can pause the video, rewind it, and see what you missed, or what I missed. All right, if you wanted to put that in your calculator from the start, we have 10 factorial divided by, here's where you're going to have to be really careful, because both of these, the 2 factorial and the 5 factorial, are both in the denominator. You have to tell the calculator with those parentheses that both of those are in the denominator. Okay? I don't know if you can hear my dog. She moos like a cow. Oh Lord, we're back to the cow things again, about cows murdering people. My dog's not murdering anything except her dog bed with sleep. Yeah, she's a pointer mix, and when she gets comfy, she just kind of deflates, and she's like, moo. No. If you hear any mooing in the background, it's my dog. All right, so we get this. Now, let me just show you that if we, oops, didn't mean to do that. So if I take these parentheses out and I typed it in like that, totally different answer. That's because the order of operations. Your calculator does that division first and then takes that answer and multiplies it by 5 factorial. So you have to tell the calculator that both of these are in the denominator, and you have to do that with parentheses. So it does make a difference here. That's why, usually I kind of encourage you, if it's smaller numbers, if you can kind of think it through and think about what's going to cancel, that might be a little more helpful. Okay, so how about you grab the calculator, pause the video, see what you can do with that one. Go ahead, pause the video, grab your calculator, you know you want to. All right, so let's grab that calculator. 100 factorial divided by 98 factorial. Overflow error. Does that mean it can't be done? Not at all. In fact, not only can this be done, you don't even need a calculator. You could do this in your head. What did she say? Yes, you can do this in your head. Let's write this out like I have the others. 100 factorial. I know what you're thinking. You're like, holy crap on a cracker. She is about to write out all 100 of these numbers. No. I don't know if you just met me or not, but no, we're not going there. So we got ... 3, 2, 1. You guys know the pattern. So that's what 100 factorial looks like. 98 factorial looks like 98, 97, all the way down to 1. So everything from, 98 down is going to cancel. So what are you left with? 100 times 99. So what was that? What was that I said about you being able to do it in your head? Yeah, you can. It's just 9,900. I like these really big ones because your calculator can't do them, and then you start thinking, oh, it can't be done. And I'm like, haha, you can do it in your head. Come over here and just circle that part. Be consistent. So yeah, those are kind of fun. Fun, right? Our definitions of fun might be slightly different. Okay, a permutation. Now, talking about rearrangements of objects. A permutation is an ordered arrangement, okay, of items where two things happen. No item is repeated, and the order is important. Okay, that's something to remember with permutation. Order is important. Okay. Now, the number of permutations of n, just however many different objects, using all of the objects, is n factorial. So that explains why I just suddenly took that little tangent over there to talk about factorials. In how many different ways can the 12 football teams in the Big Ten Conference finish? Yes, there are 12 football teams in the Big Ten Conference. Don't get me started on that. So how many ways can they finish if we're going to use all 12 teams? Well, I mean, if you think about it, the order is important, right? You have first place, second place, third place, fourth place in the division. So if we use all of them, first place, we have 12 choices. For second place, we then have 11 choices, because you're not going to have repetition. You're not going to have, like, you know, Ohio State being first, second, third, fourth, even though, you know, they think that they should be. The University of Alabama is going to be first. Roll Tide. So this right here explains this. So we are rearranging, no items repeated, order is important, 12 things. So this is just going to be simply 12 factorial. All right, so what number is that? I can't do that in my head. I wish I could. That would be a nifty party trick. All right, so 12 factorial is, man, that's a big honking number. 479001600. 479,001,600. Whew. Now, let's look back, okay, at the same example. Let me scooch this up a little bit. How many ways are there to have just first and second place finishers? Okay. This one used all 12 football teams. Here, I'm just using 2. So, we have first place, and then we have second place. How many choices do I have for a first place team in the Big Ten Conference? Well, there's only 12 teams, so I've got 12 choices for first place. Yep, even you, University of Illinois, even you get considered. Second place, we're not going to have the same team, so we're not going to have repetition. So now we're down to 11 choices for second place. Now we're going to stop here because I just asked for first and second place. So it's just going to be 12 times 11, which is, what, 120 plus 12, so 132? I know some people have their multiplications facts memorized, but not I. That's too hard. If I had asked for the top 1, 2, 3rd, first, second, third place, then I would have said 12 times 11 times 10. So these are things happening in succession, so I am multiplying them. Now, the permutations of n total objects taken r at a time. So the one I just did was 12 teams taken 2 at a time. That's n over n minus r. So n factorial, that was 12 football teams in the Big Ten Conference, divided by 12 minus 2 because I took the top 2 teams. So that was divided by 10 factorial. Okay. I know you're not about to be shocked when the answer is 132, just like it was last time. Because think about it. That's 12 times 11 times 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Divided by 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So it's just 12 times 11 because everything from 10 on cancels. So that's why we're able to just take this subtraction, because that we know that everything from there on is going to cancel. Okay, so let's look at the next one here. So now that we've got this nifty skippy formula, let's see how that applies to example 6. So pause the video, see what you can do with this. Okay, so in how many ways can a president, vice president, and treasurer be chosen from a class of 45? This is a total of 45 students, and this is a permutation taken 3 at a time. Where did I get 3 from? Well, president, vice president, treasurer. That's no different than first, second, third place. We write it with this notation. This is written 45 P3, or permutation of 45 taken 3 at a time. I could have done this exactly like I did the last one, where I did first, second, third place. I'm just going to show you that they're the same thing. Now, with this one, this is the same thing as (45) times 44 times 43. So why am I subtracting 1 each time? Because I can't have repetition. So I'm going to get 45 times 44 times 43. So I get 85,140. Now, get this. You can skip this step. If you didn't want to do this, you could use the calculator and go straight from this expression to this. So on the calculator, you would have to hit 45 and then the math button, over to probability, down to the second option that says NPR. Then you're going to have to hit enter, 3, and then enter. So I'm just trying to type out all of the syntax here, or sorry, write out all the syntax for you that you're going to have to type. So this is what's called the syntax. It's what you're typing in the calculator. So I am going to do it with you, but I wanted to go ahead and show you as well. So you have to hit the 45 first. And then this NPR formula is under math, probability. So might remember this from such hits as random integer and factorial. So we have NPR. You can't hit enter yet. You need to put in this 3. Then you can hit enter. And boom. So it's whichever way you're most comfortable doing it. If you're more comfortable with, using the calculator with this NPR business, you can go straight to the answer if you want to do it this way. Now, I would not advise you to do this approach. If, say, you had, 12,000 students, and you were looking to, say, pick 8,427 of them, probably not want to do it this way. So this would probably be the better approach. Okay, so let's notice something here. In this formula, this NPR formula, if we take n total things and we use all n of them, we said that over here, that if you use all n of them, it's just going to be n factorial. So NPN, if I use this formula, I get n over n minus n factorial. Look at that. We got that 0 factorial right there. So you see that? So what we do is, since that 0 factorial shows up and we're just like, whoa, what are we going to do with that? Okay, well, you know what? Just to make everything else make sense, we're just going to define that to be 1. That's all. So that's where that definition comes from. Here, I'll give that a little highlight just to connect it because I'm a color coding kind of girl. All right, permutations of duplicate items. The number of permutations of n items where p of them are identical, q of them are identical, r of them are identical, etc. is this. So we get the number of permutations, and we're just simply dividing out the repetition. Okay? So let me just show you with an example here. In how many ways can we rearrange the letters in Illinois using all the letters? Okay? So we have this rearrangement of duplicate items. So let's see. What's our n? N is the total number of letters. So 1, 2, 3, 4, 5, 6, 7, 8. Tell me about the duplicates. Okay? Now the P, Q, and R represents any duplicate letters that you may have. So let's say that P represents, let's see, I is a duplicate letter. How many I's are there? 1, 2, 3. L, so let's say that's Q. There are 1, 2 L's. What else? Is that it? That looks like it. I hope that's it. So, following this formula, the number of ways that we can rearrange these letters is 8 factorial over 3 factorial times 2 factorial. So take a second, pause the video, and see if you can figure out what this simplifies to be. Alright, let's see, that's going to be 8 factorial divided by 3 factorial times 2 factorial, which is just 2. So I'm just going to skip putting the factorial symbol because 2 times 1 is just 2. So I get 3,360. Different ways that we can rearrange these letters. So the P and the Q and stuff, that's just however many items you have that are repeated. If I had another word, like say Mississippi, that had, you know, the I's, the S's, and the P's that repeat, then I would have a P, a Q, and an R. So it just depends on how many different, different repeats we have going on here. So we've got I repeating, we have L repeating. All right, so we talked about permutation. So next up is a combination. A combination is very similar to a permutation. It's an arrangement where no items repeated, but here's the thing. Order is not important. That's the big difference between combinations and permutations. Okay? Now, the number of combinations of n, things taken r at a time, is given by this formula. It's really just the permutations with all of those repeats taken out. Because order now is not important. So you don't have first, second, third place. You have more like a committee of 3 people. Order is not important. Okay? So the thing to remember, this is the key. Okay? This is it. Permutations, order matters. Combinations, order does not matter. I had a student once tell me that she remembered this because she said that when you get a perm, that the order in which the chemicals go on your hair matters. So for some reason that just stuck with me over the years. I'm like, oh, okay, I can kind of see that being a cool way to remember it. Okay, example 8. Label the following as either a permutation or a combination. So really, I'm just asking you, does order matter or not? Pause the video, see if you can label these as permutation or combination, and then I'll do it and we'll compare. All right, so choosing 6 volunteers for medical research. Would you say that's a combination or a permutation? Do you think order matters or no? No, an order doesn't matter here. It's just just 6 volunteers. So that would be a combination. An 8-character password. Do you think order is important here? Oh, absolutely, order is important. If you get those letters out of order, it's a totally different word. So that's a permutation because order is important. The 3-digit combination to a combination lock. You might be thinking, well, it says combination in there twice, so it must be a combination. You would be wrong. It is a permutation because order is important. If your combination to your locker is 5, 10, 15, and you put in 15, 10, 5, it will not open because order is important. So it should be called a permutation lock. The top 5 finishers of a race. That's a permutation, right? Because the order is important. So permutation, order is important. Combination, order is not important. All right, example 9. On an exam, you must pick 2 essay questions from 6 essay questions. And how many ways are there to choose 2 questions? It really doesn't matter about the order, right? Because all you have to do is just pick 2 of them. So because order doesn't matter, this is a combination. You have 6 total and you're picking 2. So this is a 6C2. Rather than using our formula, we can just use the calculator. Now just like we did with the permutations, we put in the 6 first. You go to Math, Probability, and you can see option 3 is the NCR. Don't forget to put the R value of 2 in there. And you hit enter, we get 15. So for this one, just to make a side note there that I used the calculator. So if you look back at this later, you don't think that, that some kind of mathematical